All right, so my name is Jacob Wiegel, and I'll also be looking at the same aluminum alloy, aluminum, silicon, tin, magnesium. Except I will be addressing, rather than mechanical properties, we're looking at surface roughness. So the scope of study is using direct metal laser sintering of this aluminum powder to produce an orthogonal array of components. And we're looking at what parameters are going to affect the surface roughness. And the parameters we're investigating include scan speed, laser power, and hatching distance. For scan speed, we have 6 different values, ranging from 800 to 1250 millimeters per second. For laser power, anywhere from 120 to 190 watts, and then for hatching distance, 0.1 to 0.2 millimeters. And then you see the other fixed variables there. This aluminum has 9 to 11% weight, 9 to 11 weight percent silicon, and there's 6 other components that are involved in the alloy. And the characterization tools they're using is this EO-cent machine, which they're using to produce the parts, which are just a 20 by 20 by 5 brick form, basically, that they're looking at surface roughness of. They used an electron scanning microscope, emission scanning electron microscope, rather, to look and just get a microscopic look at what the roughness looks like on the surface. And then the MAR perthometer M1, which is a fancy machine that looks at evaluates the surface roughness, and we'll see a plot of those results later. So what is the effect of these process parameters? So this is just like the statistical results that you see. They didn't actually present a graph of physical roughness data for this. They just showed this SN value that's on the y-axis here is kind of the statistical representation of what the surface roughness is. So at a lower SN ratio, that indicated a decreased surface roughness. So you see for the leftmost graph there, for scan speed, your lowest value of scan speed is a 900 millimeters per second. Your lowest power, laser power, produced the lowest roughness, and then also your lowest hatching distance produced the lowest roughness. And I was just looking at there were 54 total combinations of tests they could have run, and they actually only ran 18 of them as part of Taguchi design. So I guess as we'll get into later, I mean, they only actually tested 18 of them, so there were some combinations that didn't get tested. However, they were still able to draw these conclusions. It was determined that all the parameters were significant for surface roughness. That's just a statistical value based on 10% alpha. And it was determined that scan speed had the greatest effect, as it had the lowest p-value in that statistical analysis. All right, so now we're looking at the effects of shot peening on the surface, which is like a post-process, cold working process where they're taking glass microspheres and just blasting them at the part. So it creates compressive stresses on the surface of the part, and it decreases, as is shown here, the surface roughness as the pressure of the process increases. So for 2 different samples here, you'll see that the reduction percentage increases as the pressure is increasing for both, up to an 83% increase for the 8 bar on sample 3. And then over here on the right, that's, as I was mentioning earlier, that's the roughness plot that they achieved. So before and after shot peening in the A and B positions there. All right, so it was determined that surface roughness could be minimized using the 900 millimeters per second scan speed, the 120 watt laser power, and a hatching distance of 0.1 millimeters, which is actually a combination that didn't get tested. So they're basing that just off the statistical representation of what would have happened had they tested it. But for efficiency and cost sake, this is the best they could do. And the best results of shot peening were obtained using a pressure of 8 bar, which was the greatest pressure that they tested. Personally, the background information was really well developed. They really got into it, started from a basic level and built it up. So it was really easy to understand. Some of the plots, especially like the statistical analysis plots, were complicated. There were 10 lines on one that it was kind of unclear what they were really indicating. And the fact that they couldn't actually physically run all of the combinations, could leave a little skepticism in the results that they achieved.